And last on the collaborations before we close the session will be Dacheng there.
Yeah, I'm here. Can you hear me?
I can hear, and you're already sharing the slide, so floor is all yours. Go ahead.
Yeah, thanks. So I'm Dacheng Xu. I'm from Columbia University. I'm currently a PhD student. This talk is about the XENONnT dark matter project, about the recent data reprocessing in it. And XENON collaboration is an long-lasting existing collaboration, consists of more than 200 members in 30 institutes around 12 countries. So we work in very different time zones. I would not have any time to discuss whether we want to look for dark matter, but we are searching for a kind of dark matter called WIMP, weakly interacting massive particle. And as an ionizing particle, we hope that WIMP can collide with the xenon nucleus. So we use the liquid xenon as a target. That is also where the name comes from. And WIMP, because it's carrying the kinetic energy, the energy will convert into the kinetic energy of the xenon nucleus. And then liquid xenon is a very good scintillator. The deposited energy will be converted into the photons that photon sensors can see. And in XENONnT, we use the photomultiplier tubes, PMTs, as the sensors. And the output of the PMT will be stored for further offline analysis. So the data reprocessing means to extract the features of the electrical pulse of the output of PMT, and eventually we can maybe we can see whether there are some excess other than the background. And XENONnT detector is a next state detector. It's under the Gran Sasso mountain of Italy. We have a outer detector to reject the muons. It is a muon veto, and inner detector of neutron veto, and innermost one is the liquid xenon TBC. You don't have to understand any principle of this detector, but it is filled with the liquid xenon, and with the vertically applied electric field, the freed electrons can be drifted to the surface of this liquid. And we look for the coincidence of two kinds of signal within the liquid xenon. The most important feature here is actually the number of PMTs. We currently have about 500 PMTs. And XENONnT is using a triggerless data taking mode, so the amount of data is considerable. There's many incarnations of xenon detectors over the recent 2 decades. From the very old detector, Xenon 10 was only using dozens of kilograms of liquid xenon, but now in the fourth incarnation of xenon experiment, we are using tons, actually nearly 9 tons of liquid xenon. So it is growing in a factor of 1,000. But the PMT is not growing in that scale because it is squared of it is in the scale of the square of the size. So the PMTs grow from 90 to 500. But in the XENON 10 and 100 and 1 ton, the data taking mode is triggered. So you only take some data when enough photon is seen by the PMT array. But now in nton, we want to push our energy threshold to lower level. We record basically everything. And for more information, please go to the website. It's a very well-built website. And the goal of the data reprocessing in nton is to extract the features of the signal from the raw data, the output of the PMTs, to the meaningful observables. The observables will perform the inference to tell whether dark matter WIMP exists. And of course, we can remove the background in various of level in this data reprocessing, and the red plot is the so-called dependency tree. And the bottom, the red one, the raw records, is directly the output of PMTs, and on the top, it is events. We will have the meaningful features there. The red horizontal line splits the tree into upper and lower level. I will refer to later. And another motivation is to compress the needed size of data. Of course, we cannot put all the raw data in the final analysis, and the comparison of the raw and final level of data is significant, because the reduction is from several petabytes to only several megabytes. So we will only see in the order of 100 events in the final data set, even in the life cycle of whole XENON. So we only look for no more than 1,000 events. And we have to store some intermediate results. So the processed data size will be in the order of 100 terabyte. So this is not about high luminosity, not about high flux, but only searching for some rare events. This is different from the previous one experiment. And this is the data flow, how the data flow from from Italy to the storage of RCC. First, the data is taken in Italy from the PMTs, and they are transferred to some Ruscio RSEs, either in US or in Europe. And those data will be reprocessed on the OSG computing nodes, and then the result will be transferred into some Ruscio RIC or the storage in RCC in the University of Chicago. I'm only talking about SENON because I'm starting to taking charge of the reprocessing only in SENON. For SENON there are someone else, and they helped in the improvement of the data flow and the reprocessing pipeline. The raw data, as I said just now, is about 4 petabyte, 160 MB per second, and the processed data is only about 200 TB. So it is also small size comparing to collider experiments. And this is just a software that we use in the reprocessing. We call it outsource. It is the wrapper of both Pegasus, which is not from XENON, it is a workflow management software, and the contacting person in XENON is Matt, who helped a lot on guiding us how that works. Outsource is also a wrapper of Straxen, the core of the XENON data reprocessing, and outsource is a combination of those two. Basically, it tells the amount of resources the Straxen reprocessing will need to Pegasus. And this is the workflow that Pegasus will submit on the OSG computing nodes. We'll have some lower level, refers to the lower level in the dependency tree I talked about. For a single run, we'll submit multiple jobs in the lower level, and they require less amount of resources, usually 8 GB memory and less than 12 GB disk. But 8 GB memory is still high, but we cannot reduce it further. It's already better than SENON. We need a combined job, cheap in memory, but high demand in the disk to combine the result of the lower level. And we have a final job called for upper level. Because the number of upper job is not so much, even though the memory requirement is same to the lower level, it does not contribute much to the resources requirement. But it is still heavy in the disk usage. After SENON, we identified some memory consumption bits, and they are killed by the optimization. So previously in science, in SR1, we use about 30 GB memory per job in the lower level, but now we use less than about 8 GB. So it's about 4 times reduction, and this accelerated our reprocessing by a lot. Roughly in the typical example of a workflow, this is the number of jobs and total memory usage evolution in this workflow. One workflow usually take less than 1 day. The largest number of job can be several hundred, and then the total memory usage has a peak value of several terabytes. And this is just the statistics about the wall time and CPU time we used and how many workflow we submitted in the recent 4 months, and number of successful lower combined and upper level jobs. So the wall time is about 50 days. So the occupancy is about 40% in the recent 4 months. And if you run on single CPU, it will take 17 years. So usually we have hundreds of CPU working concurrently. And as a conclusion, we just had an overview about the N-ton SR2 reprocessing, and it is greatly benefited from the support of the OSG collaboration. And now we have a reprocessing pipeline that know how much resources it is consumption and it is consuming. And in the next generation of liquid xenon TBC dark matter project called XLGD, it is actually the combination of the 3 existing mainstream liquid xenon dark matter TBC experiment. We'll have more than 1,000 PMTs, so the amount of data will increase by several factors in the next decade. And I want to take the chance to say thank you to Pascal and Judith from RCC, and also Mass, and also other contributors to OSG. Thanks.
Reminder, we're not RCC. Sorry.
Sorry, I did not get that.
We were not RCC, just letting you know, just reminding you again.
Right. Yeah.
Is not the XLGD experiment, is it going? Because there's another dark matter proposed experiment that was kind of like advertised as the replacement for xenon here, although, are you aware, does this ring a bell?
Sorry, Pascal, I did not get that.
There is an experiment called Doorway. Which is it was advertised as a replacement, eventual replacement for xenon. Is this the same one here, the XLGD, or this is a different one?
Actually, I don't think this is publicly announced, but effectively Darwin works as a R&D experiment for XLGD, so it will not provide any dark matter search result. So there will not be any liquid xenon field in the Darwin detector. There will not be a Darwin detector.
Thanks. Any questions for the chair? What I was going to ask is, when you're doing the SR, so can you kind of like give us some, what happens to the computational workflows, memories and storage when you guys are doing the data gathering campaigns? All of a sudden we are hitting the ratio endpoints really hard, gathering a lot of data and kind of stressing out the infrastructure. How often does this happen?
Oh, you mean the transfer failure between Ruscio and OSG nodes?
Yeah, and how does this correlate with the data gathering campaign? Sometimes you just go and you gather a lot of data at one time. You put it on, what is it, recalibration campaigns or calibration campaigns or something like that.
Oh, well, this diagram only covers the offline data reprocessing. And of course, yeah, in the XENON calibration campaign, there can be some cases that the ratio uploading fail, and then the data are just accumulated in Italy and cannot be transferred, and we have to stop or no, pause the calibration. But this, I mean, I feel that in SENON 2, this happens less than SENON 1. We have more diagnostic scripts to tell why the uploading is failed. I don't know whether this is your question, sorry.
No, it is my question. What I'm trying to highlight is the continuing improvement, even during the times where in the past you had challenges. It doesn't mean that you don't have challenges this time, you just learn to adapt. And, it looked like the latest calibration campaign did not have as many problems as it was like a year ago. Was that correct?
Yeah, I think yes. Yeah.
That's the statement I was willing to get out of it, that, there will always be problems when we're stressing the infrastructure, but as long as we adapt and take the lessons and move on, it gets slightly better, right?
Right. I still see some problem that to resolve in current pipeline, but this one works. So we just run like that.
All right, thank you, Dacheng. Any other questions for XENON?